Right, in this video we're going to look at motion with uniform acceleration and derive some formulae. These formulae are very important. So when considering motion of objects with uniform acceleration or constant acceleration, we need to consider the following variables. S is displacement. Displacement is distance from a certain point. U is the initial velocity, V is the final velocity, and A is the acceleration, which is constant, and T is time. So consider the following velocity time graph. So we've got a velocity time graph here. This is time and this is velocity. We've got an initial velocity here of U and a final velocity of V. Okay, and it travels in a straight line. This is a straight line, which means the acceleration is constant, uniform. The acceleration will be given by the gradient of this line at time t. Right, the graph of the gradient of the graph gives acceleration. So A will be V minus U divided by t. So the change here divided by this distance here. This distance is t, and this here is given by v minus u. And then if we rearrange that, we're going to get that v minus u is equal to at, and then we get that v is equal to u plus at, which is the first equation that we need to know. Right, now considering this, if you now consider the area as a trapezium, so the area underneath the graph, now the area underneath a graph of velocity time graph here, this area here, gives us displacement. So if we consider this a trapezium, so this is one side and this is the other side parallel to it, this will be considered the height, so you might want to turn this round on its side. The area of a trapezium is a half of this side plus this side, so it's half of u plus v times the height. This is from the area of a trapezium. Right, if we now take this and substitute v is equal to u plus at instead of v in this, we now get that s is equal to a half bracket u plus at times t. So working with it, we're going to get a half of 2u plus at times t. Then we're going to get a half of 2ut plus at squared. Taking that half in, we end up that the displacement is u times t plus a half at squared. So displacement is the initial velocity times time plus a half times the acceleration times the time squared. Doing a similar sort of substitution for so rearranging this, we get that u is equal to v minus at. We substitute that into this. We're going to get that s is equal to a half of v minus at instead of u plus vt, and then we end up with s is equal to vt minus a half at squared. And finally, if we now substitute t is equal to v minus u into a half of u plus v times t, this gives s is equal to a half of u plus v times v minus u over e instead of t. So you can get t by rearranging v is equal to u plus at. This is where this comes from. So that's going to give me, if we expand this times this using the difference of two squares, we're going to get v squared minus u squared over 2a from this 2 here. And then rearranging that, we're going to have 2as is equal to v squared minus u squared. And then we have the final velocity squared is equal to u squared plus 2as. Right, these complete list is given below are the only valid if the acceleration is uniform, i.e. the acceleration is constant. And we've got v is equal to u plus at. So we've got s is equal to ut plus a half at squared. V squared is equal to u squared plus 2as, and we've got s is equal to a half of u plus v times t, and s is equal to vt minus a half at squared. Okay, these are known as the Suvat equations. I hope you've understood this video. So what we've done is we derived all the Suvat equations. I hope you've understood, and I thank you very much for watching.